Oh, hello. I was just counting my money. Hi, everyone. Welcome to section 2.5, quadratic regressions and word problems. You've probably heard of regressions before. Regressions are lines of best fit. And when you were in Math 1, I'm sure you did a lot of linear regressions. So in Math 2, we piggyback off of that and we do quadratic regressions. And we're going to be looking at word problems, yes, applications, real life things, based on the regressions that we get. Now remember, a regression line is just a graph. It's just a line that's the best line that goes with the data points that we get. Some essential questions. What is a quadratic regression? How is a quadratic regression calculated? And what are the key points needed to answer application problems? I wanted to add one with you just to emphasize another essential question that is going to be one of the super important ones, okay? And so how is a realistic domain determined? See, we're going to be looking at real life scenarios. And so when we talk about domains like we've been doing, it's just negative infinity to infinity. But if we're talking about realistic scenarios and we have an upside down parabola and we're talking about time, we can't go in the negative realm with time. So our domain will not start with negative infinity. So that's one of the super new types of essential questions. So let's buckle up and get ready. All right. Now, this is really just a formality. Yes, we have these calculators, and yes, I said we need to get really used to them. And I was going to go all out, and I was going to do all of this on the calculator, and then I really decided against it because, well, you'll see. But anyway, I still want you to know the steps on how to find a regression in the calculator. I know you learned it last semester with linear regression. It's the same thing, except over here, instead of going to number 4 for linreg, you go to number 5 for quadreg. So on note card 62, I want you to put these steps that I outlined in yellow on how to find a quadratic regression in your calculator. Pause me and finish up note card 62. All right, so now that you have that out of the way, and I know you know how to do it, if you need some more help with that, let me know. We are going to be actually going into Desmos and spending a lot of time in Desmos. I'm going to put a link on the working document. I noticed that some of you are not using the North Carolina test version of Desmos, and I want you to do that. Okay, I need you to get used to using that. That is what you will use on the Math 3 EOC next year. And so I don't want you just to use the generic version of it. I want you to get used to using the NC test version because it's a little more limited, but that way you know what you have access to when you take your EOC next year. All right, so I found this video of this other teacher, and she does a great job explaining. So I am going to play this. I'm not sure if you're going to be able to hear it very well. So if you don't hear this, you need to go into the slides that I link out to and watch it. This video is on the slides. Okay, so she does a really good job explaining it. Of course, I could do that too, but I thought I'd give you a different perspective. Um, so this is how you do it. This is how you do it. Now, I'm pretty sure in Math 1 you knew how to find a linear regression in Desmos. The only difference is you don't just put ax plus b. You have to put the standard form of a quadratic, the ax squared plus bx plus c, and you have to have, you know, the X1 in there. And I'm going to go over that several times. I just popped in the video here on this slide as well, but here's your note card 63, where you write down how to find a quadratic regression on Desmos. Okay, so hopefully you're getting that going. Pause me if you need to and get this note card finished so we can jump into how to actually do this ourselves. All right, so I want to jump in with an example for you. I don't want you to write this down. This is not a note card. This one's not. I want you just to watch, engage, watch what I'm doing. Um, Rewind me if you need to, if you get a little confused. But we got this. We've got this. It says an amusement park ride takes riders to the top of a tower and drops them. Have any of you ever been on one of those? I have. I love it. The table below shows the height h, so here's the height of the tower, at the time t seconds after the drop. Okay, so t is the seconds after the drop, so it started at 0 seconds, it was 200. Now it's not telling me units, but I'm assuming feet. So at 0 seconds, it's 200 feet high. At 0.5 seconds, it's 164 feet high. After 1 second of dropping, you're 120 feet high, and so on. So I need to take this information and I need to put it into Desmos. So I'm going to go to Desmos. I need to, I know you can't see this. I can't extend my window. Maybe I can. Maybe it'll let me. Oh, it will. Yay. Okay. So I'm going to go to this plus, and when you're in the NC test version, it doesn't have all those other options, but it does have the table option. So I need to go back and look. Let's see here. What can I do? Oh, there it is. All right, so 0, 0.51, 1.52. So I'm going up by 0.5 increments from 0 to 2. And sometimes it's just the transferring the numbers here that you can get messed up with. So just double check, or I can too, just double check that you type that information correctly. Now I've got 200, 164. Need to make sure that I'm typing the right information with the right data. Yes, the 200 goes with the 0. Yes, the 164 goes with the 0.5. Okay, then I have 120, 68, and 8. 120, 68, and 8, just double checking. Okay, so if I want to find my regression, oh, yeah, okay. I had an extra row there. So if I want to find my regression, I just type Y. Now, I look up here, and Desmos has named this data. They've named it X1 and Y1. So I have to be very specific down here, and I have to put a 1. Now, it'll automatically make it a subscript for you, so you don't have to worry about that. But I have to do that because otherwise it's some generic Y. We're talking about this Y1. This is you assigning Desmos to look at this data. Then I have to use a little squiggly. It's in the upper left corner of your keyboard, and it's next to the 1. So you hit shift, that thing. And then this is where you put the standard form, and you do AX, but it's got to be X1 because X1 is our label there. And then we need it squared, and then plus BX1. Okay, you cannot forget those or it will not work right, plus C. So here's my regression line. Here are my parameters it's giving it to me. And so when it's asking me in the question, what is the, well, let me go back so you can see it. I'm just going to copy that real quick. It says, okay, here we go. Write an equation. So we have to use those parameters to write the equation. I'm going to copy those. Are you sure I took a picture? Oh, there it is. Okay. So I'm just going to plop that up here. I know it's covering up some things, but that's okay. So when I go to type this in or whatever form I'm asking you to do this on, you don't have to write the squiggle and the ones and the subscript ones. This is just our linear regression. I'm sorry, quadratic regression. So it's y equals, our parameter of a is negative 16, x squared. You're going to see a negative 16 because that's the gravity pull on Earth, just saying. All right. Plus, and then b is negative 64. So really, I'm going to backtrack and just put minus 64x, and then our c is 200. Your c is always, always, always your starting height of the thing, of whatever you're looking at. So the starting height is 200. And I'm going to go back to Desmos and look at the graph. Now, you might go, well, Ms. Sharp, I don't see the whole parabola. No, you don't. You're going to have to zoom in. You're going to have to click and drag, and it's going to be a little uncomfortable because we're used to all of this being nice and pretty in our window, and we can see everything, and it's just wonderful. But with these word problems, we have to be careful. Now, I can go over here. You can't see what I'm doing. Okay, I can go over here to the wrench, and I can change some things. I can adjust my X and my Y values, all of that. Reverse contrast. Oh, wait, I could do that too. Anyway, I'm not going to, but I know that I need to go up to 200 because in this regression, my C is 200. And it's really, really hard to see. But there is a parabola. There it is, okay? And it crosses the y-axis at 200. Its maximum is over here in the negative realm, and that's not applicable. That's not part of the realistic domain. This thing starts at a height of 200, so it starts right here, and then it's going to go down and hit the x-axis after at 2.062. So a lot of times the hard part for students is understanding what they need, what part of these graphs they need. I'm trying to pause this thing and it's being wonky. Oh, it's up there. Okay, so we just saw where I had this little bitty sliver and it was hard to see. So what I did was I went to the wrench, okay, and I knew that what I did here was I hit Control A there and I put a 0. I don't need to go to the left. Oh goodness. I don't need to go to the left of 0 on the x-axis. That's not a realistic domain. And I had looked and I saw that the x-intercept was 2 point something, so control A there and make that a 3. And I know that on my y-axis, I'm not going to be going below, so I'm going to start at 0. And then I know my maximum there was, well, my highest height of this tower was 200. That's where it started. And I changed, if I keep the step here at 1, I could. It's just going to be really hard to see. I'm going to change the step to 200. When you're dealing with hundreds, the step is how much each little line that you see goes up. So I just changed around and I can see the part of the parabola that I need. Now I'm going to zoom out just a little with my keypad. And then I'm just going to click and drag up a little bit. And this is a perfect viewing window for what I wanted. So I'm going to go back. I need this point 200. And look, they're giving me some other points. Those might be important. And then that point, and then I'm going to go right here and get that x-intercept. So this part, the controlling your graph might be tricky, but it's super, super important. I'm going to take a screenshot of this, partial screenshot, because we are going to be referring to this as we answer these questions. I'm going to go back right here, and I'm going to, there we go, I'm going to take this one away now. We don't need it. I'm going to shrink this up a little bit so we can see it a little bit better. Move around. I know this is like technical nightmare. Okay, so I'm going to move this over. I'm going to put this over here, maybe. That's not wanting me to do that. You know what? I'm glad that you guys get to see that I'm human too, that things just don't always work out the way we want them to, but that's okay. All right, so I'm going to put this right here. I'm going to have to move it around, but that's okay. We've got the equation. I've got the part of the graph that I need. Super important. Now, part B. It says, how many seconds will it take the tower to reach the ground? See, this is the height of the tower, and then, so the y value is the height. So when the height is 0, that is when you reach the ground. So the ground is when the height is 0. That's super important. You need to know that. So when I look at this information, these key points that I got off of Desmos, when y, or the height, is 0, that's 2.062 seconds. So that means it took 2.062 seconds for the tower to reach the ground. Okay. I mean, so that ride was short. Yep. And those rides are short. I'm actually going to change this right here to 1.5 seconds. Okay. So now the question is, how high is the tower after 1.5 seconds? And guys, I have that as one of the points that it just gave me. So after 1.5 seconds, it's 68 feet high. So look right here, 1.5. So you'll see that I answer these with sort of complete sentences. I mean, they might not be grammatically correct, but you need to do that. Right here it would be, hold on, it takes, I don't know why that was being wonky. Okay, so back over to C, part C. How high is the tower after 1.5 seconds? The tower is 68 feet above the ground after 1.5 seconds. I imagine like the drop zone, like a game like that, like a ride like that. And so you would be 68 feet above the ground only after 1.5 seconds. So it's going pretty fast. Now, the next question is, what is the height of the tower before it drops? So before it drops, we could look right here and get the answer. But before it drops, that tower is sitting at 200 feet. The tower is 200 feet above the ground before it drops. So of course you could get more thrill from the ride if it were higher up before it dropped. All right, so that's a great example. We're going to move on to another example, and this one is note card. But I really, really, really would like you to take it all in. You can pause me throughout the example if you would like, but rewind me, listen to me again if you need to, because this is a lot of information, a lot of technical stuff on Desmos and how to find the window and things that you need. But it's super important. Oh, you know what? I keep saying super important. Y'all are probably like, Miss Sharp, we hear you. Okay, stop saying that. I want to add an E on here. I just do. What is the appropriate domain for this situation? So the domain for this situation, so we wouldn't say, yes, it's a parabola. Yes, I told you that, parabola's domain is going to be all real numbers, but not when we're talking about a situation like this. So what is the appropriate domain for this? Well, we can't go over here to the left because that means times would be in the second quadrant because time would be negative. And then after it hits the ground, there's no more. So the appropriate domain is time of 0 seconds all the way to time of 2.062 seconds. That's the appropriate domain. And I can even go a little further and say, what is the appropriate range for this situation? Okay, so the appropriate range for this situation, while I'm getting this arranged, you think about it. Think about what you think that might be. So we know we go bottom to top. Normally we would say negative infinity up to whatever that maximum is, but it's not going above 200 feet and it's not going below the ground. So what is the appropriate range? Well, the bottommost y value is at the ground, which is 0. And the topmost y value is where it's sitting at 200 feet. So there's your appropriate range. All right, now we're on to note card 64. Yes, and it's a different example. Braden jumped off a cliff and into the ocean while vacationing in Hawaii. His height h after time t seconds is given in the table below. And guys, the heights in feet, normally they tell you the units. I'm not sure why. I grabbed this problem that doesn't tell you the units, but the height would be in feet. We're going to be doing all kinds of things on this. So again, you can decide, just watch me all the way through this example and then put it on your note card, or as I'm doing different things, just stop and put it in the note card. So the first question it's asking for is, what is the equation for the curve of best fit? That is a regression. When they say a curve of best fit, that's a regression. These are quadratic regressions. So I'm going to go to Desmos. We've already typed into Desmos. Our Desmos has got settings going on. It's got things going on. So we got to be careful here. I'm going to go and take these things away. And I need to insert a table. I need to look back at this, 0, 1, 2, 3, 4. Okay, oops, see, I already messed that up. I need to fix that, make that a 0. Always check yourself. And then 480, 482. 452, 390. And 296. And then I'm just going to make sure that I typed all those in correctly. 0, 480, 1, 482, 2, 452, 3, 390, and lastly, 4, 296. I did. Okay. So to get my regression, I go right here. Remember, I've got to tell it Y1. So I type Y, hit a 1. It'll just make it that little squiggle. And then my standard form, AX. Now, if I forget to put the 1, I want to show you what's going to happen. AX squared plus BX, because we know this. See, and nothing is popping up below because we're not telling it to use this data. So I got to go back after the X and put a 1. After this X and put a 1, because X's and Y's were assigned a role in Desmos and we have to tell it. So here's my regression. I'm going to go, just for ease for the presentation here, I'm going to go and plop that over here so we can see it. And it wants me to write the equation down, so we can do that. Move my face. There, it'll let me do that. Okay, so the equation is, I don't know why I care so much, but there we go. Y equals, now A is negative 16. You're going to see that. And you can even put, you know what? I want you to put H equals, because we're using H and T. So H is Y. So H equals the height equals negative 16 T, because T is our X, it's our time, squared. Look, negative 16 is the parameter for A. T squared plus the parameter for B is 18. So 18T. And then plus 480. Guys, you can put X's and Y's if you want. I just want you to see that we are looking at different variables. H is the height, T is the time. How long will it take Braden to reach a height of 150? And guys, you could put 150 in the H and then solve using the quadratic formula, tossing the 150 over, blah, blah, blah. Or you can just learn how to use Desmos and learn how to use the graph. So over here in Desmos, I am not even seeing the graph. I know that the y-intercept's 480. Ah, there it is. There it is. And I had already changed around things, and I'm kind of liking what it's looking like because I can see it. So here we go. There's the 480. They're giving me a few other key points. I think they like to go to integer values of time. And then I'm going to click right here and get that. Okay, so I'm going to grab this, do a partial screenshot. That 480 is in the second quadrant, just where it typed it. I don't like that, but that's okay. All right, I'm going to bring it back right here. Need to shrink it up. Blah, blah, blah. Okay, so there's the graph. There it is. And keep in mind, I don't really need this area over here in the second and third quadrant. It's just it typed the 480 right there, so that's why I grabbed it. I'm just looking here. Here's the cliff that Braden's on. This is the cliff. And then he jumps and gets in the water. Okay, so how long will it take Braden to reach a height of 150 feet? Now I could guess what I think it is. It's somewhere in here. So 5 point something, because that's 4 seconds and that's 6 seconds. 5 point something. But this is kind of tricky. It's asking for a specific height. I see a height of 452, 296, and 0, and none of that 150 is not on any of that. So I need to go back to Desmos, and let me show you what I'm going to do. I want a height of 150. So I'm going to go right here and put y equals 150 because y is the height. And look, it drew a horizontal line. And see, here's Braden jumping off. And it wants to know how long it takes for him to get to a height of 150. So by me typing in y equals 150 right here, it generated a point for me. And so it's going to take 5.139 seconds for that to happen. Pretty cool, huh? So you have to know how to do that. You have to know what I just did. The height is y, or h, and I just put y equals 150. It drew in a horizontal line for me, and then I was able to click right here and get the value that I needed. Pretty cool, huh? I think so anyway. How long until Braden hits the water? Well, this is already on here. It will take 6.069 seconds for Braden to hit the water. So he's only in the air after the jump for 6.069 seconds because the water here is like the ground and it would be 0. How high was Braden after 5 seconds? Now, it didn't actually give me that right here. It gave me 1, 2, 3, 4, but not 5. So let me go look after 5 seconds. I don't know why it didn't do that. Look, I can guess. I could guess what it is, but I don't know. Now I'm going to go clear off this y equals 150, and now it's asking for a specific second. So I need to not put y equals, but x equals. It wants after 5 seconds. And so I'm going to change that color. Probably will, but I'm not sure. Okay, so here is the x equals 5 line. It just drew it in for me. And I look right here. So he will be 170 feet up after 5 seconds. After 5 seconds, Braden is 170 feet high. Okay, now again, I had to go to Desmos and type in x equals 5 because x is the seconds, x is the time, and that gave me what I needed. Another way you could do it algebraically is just put 5 into your regression line right here. I could just put 5 in the t-spots and it would give me 170 after I evaluate it. I think it's easier on Desmos, but you could do that. All right, what was the initial height of the cliff where Braden jumped off? Well, that's your C. Your C value is 480, and you can also look at it right here. And you can also see it on the graph right there that he was starting off at 480 feet. I typed too fast and it's like, look, I have to delete. It's like become a habit. All right, so what's the domain? You know, time can't be negative, so you're never going to have a negative infinity in the domain on these. So you know your domain is going to start with a bracket 0, because that's time equals 0. Then he hits the water, okay, at 6.069. So that's your domain. What about your range? Your range. Yes, he can go below the water, but we're really talking about his time in the air, okay, for the jump. And so your appropriate range, that's why I was using the word appropriate, is bottom to top would be 0 up to what? Not 480 because he jumped up off the cliff. He jumped up. So the height right here, let me go back to Desmos, make sure I have the right thing. Yeah, this is actually, if I zoom out a little bit, this is the height, you guys. You might mess this up, but the maximum. The maximum when you've got parabolas, it's got these other key points. I'm going to exit out of that. Those, oh goodness, I didn't mean to do that. Undo that. Okay. Those points are actually, I realize they're actually these data points, those blue points. But your height, when you click those blue points are the data points, but when you click the parabola, your height's going to pop up right there in the middle. So his maximum height is actually 485.063. So that's really his range. And you guys can probably already tell that might be a problem spot for a lot of students because they want to put 480, or they would want to put 482 because that was one of those points that was just on there, right there. I click away and go right there. You might just want to put, but it gets higher in between those two. You can zoom in and see I mean, I could really go to town and really zoom in and see that those two data points that were given on the table, yeah, are great, but there's a maximum point in between those. Okay? So just be careful. Now's your time. If you haven't finished the note card, to pause me and go finish this note card. I do recommend that you draw a little graph of the first quadrant and have it in there. You don't have to have all of these little points, but just kind of to realize that's where I got the information. So I'm trying to figure out where to put this. Put it right there. Braden, that says Braden, and that says T seconds. All right, so pause me and finish up this one. All right, this next one is not a note card. I just want to go over it with you. And here we go. Write an equation for the curve of best fit. So I've got my Desmos going on. I need to delete this stuff. I need to go and add a table. Look back here, 0, 0.5, 1, 1.5, and 2. Okay. And then 50, 64, and 70. 50, 64, 70. Oops, see, I already messed up. 50, 64, 70. Let's go see what these other ones were. 68 and 58. All right, so now I need to tell it to do the equation, the quadratic regression. So y1 equals ax1 squared plus bx1 plus c. There it is. There are my parameters. And, oh, there we go. I'm just zooming around trying to get what I want here. Okay, because I want to be able to see. Okay, remember, these are the data points that I put in the table. I'm going to get that. I'm going to go over here and get this one. And then this gray one is the maximum. Those data points are in purple. I'm going to go plop this on here. Good spot for it right there. Okay, and then the actual curve calculations are right here with the parameters. All right. So now I'm going to go and answer some questions. Put that right here. I know it's in the way a little bit, but it'll be fine for now. So what is the equation of the curve of best fit or the quadratic regression? It's y equals, looking at the parameters, negative 16. Oh, I'm going to do h equals. H equals negative 16 t squared. And I'm looking right here, plus 36 t plus 50. If you're not ready to use the t's and the h's, that's okay. That's okay. I think it's a good habit, but if it's just really wigging you out, don't worry about it. This is Sarah. She's standing on a bridge that stands 50 feet above the water, hence the reason why C is 50 and we have 0, 50. She tosses a coin into the water. Have any of you ever done that, like a wishing well or just in general tossing it into water? The height h of the coin at t seconds is given in the table below. We are talking about heights of in feet. So we did this. There's the curve or the regression. What is the height of the coin after 3 seconds? And I don't know. I don't know. So I need to go back to Desmos, and it wants after 3 seconds, which is t, which is x. So after 3 seconds, I mean, I could guess I could like try to move my thing right at 3, and sometimes you're lucky, and sometimes you're just, and I'm going to be super picky. I need to have decimals. They need to be correct. So I need my x to be 3, okay, because we're looking at time. So I just put an x equals 3, and it's going to generate that dot. So how high is it? That coin after 3 seconds, it's 14 feet. Okay, what is the maximum height of the coin? Now, I had some forethought and I already clicked it, but just so you know, those purple ones are the data points. I'm going to click the actual parabola. The gray points are those key points. So 70.25, and I have it right here. The maximum height of the coin 70.25 feet. So she got that to go up some. She was standing there at 50 feet, so all right. After how many seconds does the coin reach the maximum height? So guys, that's after 1.125 seconds. After 1.125 seconds, it reaches that maximum height. I have that right here. Okay. How long does it take for the coin to, let's see, to hit the water? You can tell I was copying and pasting. So how long does it take for the coin to hit the water? Hits the water. So it's going to take 3.22 seconds. Okay. I wanted to add in appropriate domain and range. So what would the domain and range be here? The in context of the problem, the domain would be 0 to 3.22 because it took 3.22 seconds for that coin to hit the water. And what about the range? Bottom to top, when it hits the water, the height is 0 because we're talking about height. And it went all the way up to the maximum of 70.25. So there's your domain and range in context of the problem. This has been a very, very long video. I did not anticipate it to be so long. It's not like it's a lot of slides, but it's a lot of explanations and desmos. I had 3 more examples. I think I might just add these as quick little 5-minute videos for later. But thank you for making it this far. I know it was a marathon to get here. I hope it's making sense. I did want to tell you that on my YouTube channel, I can't believe I'm saying that, but the little thing where I've been doing the videos, I have old videos that I made in 2016 and it was actually on this stuff. Now I look very different, my hair's short. I'm teaching in a different way because it was a long time ago and we didn't do this on the computer. But you guys go check them out if you're really struggling. Also, did you make it this far? Send me an email. And in the email, I want you to put stapler. And I'll explain stapler and why I'm having you put stapler later. But in the email, in the subject line, put stapler and you'll get a couple, 1, maybe 2 extra credit points on the next checkpoint. Thanks, guys.